Hello everyone, welcome to the linear elasticity class. In this video, I'm going to continue the topic that we started before regarding the kinematics of the continua, and now we're going to move to the strain representation in spherical and cylindrical coordinates. Now what we're going to do, I'm just going to show you how we can represent the strain and the rotation tensor in the cylindrical coordinates and the spherical coordinates. So what about the cylindrical and spherical coordinate? We didn't discuss this part in the vector and tensor calculus, but they are very important. In many cases, for example, what we were describing the strain up there, we were referring to x, y, and z. These are the rectangular coordinates, right? But generally, and even you have an experience in these things in the physics class, even in the mechanics and the dynamic class. For example, if we do have, like, this is y coordinate and this is the z and the x coordinate, and we do have here the z coordinate, and let us choose a point, pick a point, whatever it is, like point A. So if I ask you to describe the position of this point with respect to the original point, what you're gonna do, you're just gonna specify an x coordinate and z coordinate. In addition, assume that this is, let us make the vertical axis z. Assume that this is z and y. Anyway, so you're gonna define an x coordinate, right, and y coordinate, and then you're gonna describe a z coordinate just to jump up to locate point A, assuming that point A is already located here. Let us remove this point, assume that point A is already somewhere, right, is already defined here. Okay, assume that this is point A. Make sense? So here we are working in, like, you're already moving parallel to x, y, and z to end up with the point. This is known as the rectangular representation of the vector, the position vector of this point. But there is another option that I can go directly to the point, and then I'm gonna use like some angles, like one angle, like initially at the initial start, like you're already standing at the 0 point and you are facing the x-axis, so you have to give a rotation. You're gonna give a rotation about the z-axis with an angle theta. Then you're gonna give rotation. Then you're gonna move in the r direction. This is like the radial direction along r direction. Or you can move like along r direction, then you're gonna give rotation with an angle theta, then you're gonna move in the vertical direction, like you're already moving in a cylindrical space, kind of. So for a cylindrical space, to describe the location of any point that belongs to the circumference or the external surface, the cylindrical surface of this cylindrical space, like any point B, for example. So you have to define, you can define the location of this point as r and an angle theta with respect to the x-axis in addition to the z direction parallel to z. So in the cylindrical coordinate, we are using 3 coordinates. Instead of x, y, and z, we are using r, theta, and z. There is another coordinate system which is a spherical, like you assume that you're gonna move in a spherical space. So this spherical space requires r and theta and phi, like 2 angles in addition to displacement parallel to the radius, like a sphere. The same thing for the cylindrical coordinate, like we are using 2 distances, like r in the radial direction and the axial or the vertical direction, which is the z direction, that parallel to the axis of the cylinder in addition to the angle, to define the location of or the position of a point. So these are the cylindrical coordinates and these are the spherical coordinates. So in some application and some types of problems, and this is what we're going to consider even after a while during this class, there are some problems that it is better to describe the displacement of a point using the cylindrical coordinate or the spherical coordinate. It's going to be much more easy and simple and makes sense more than describing them using the rectangular coordinates as x, y, and z. So generally we do have 3 different types of coordination of points, like x, y, and z. As I mentioned, this is known as the rectangular coordinates, and we do have the r, theta, z. This is the cylindrical coordinate, r, theta, phi, which is the spherical coordinate. I won't gonna go through the transition from the rectangular to cylindrical, or cylindrical to spherical, or rectangular to spherical. I won't gonna give you these things because it's gonna take time, and we already have a problem with this, like we already running out of time for this part. But anyway, if you are interested, I can give you some material, even I can explain to you how we can convert from rectangular to cylindrical coordinate or rectangular to spherical coordinate. But the thing that I'd like to demonstrate here, that we are interested in finding the strain in the cylindrical coordinate, the same thing for the rotation tensor, but let us focus on the strain, and this is the important thing, and that's why I'm going to present here the strain, how we can drive it or represent the strain in the cylindrical coordinate very quick. All right. So we define the strain in the vector in the vector form, like epsilon, it should be the 1/2, the nabla u, which is the gradient of the displacement, plus the nabla u transpose, right, which is the transpose of the displacement vector kind of, which can be written also this term. It is better to write this one as 1/2 the nabla u plus u nabla. So this u nabla, this is gonna work like you already switching kind of, or doing the transpose of the displacement gradient tensor. So anyway, it means that to form the strain, you should find the gradient of the displacement vector. The displacement vector is just a vector, right? So if we said that a vector like this one, like u as a vector, in the rectangular coordinate, we're gonna represent this one as ux, uy, uz, which can be written as ui delta I, but you should understand that I in this way, it will be once x, y, and z. This is in the rectangular coordinate, right? The other option is, if we decided to represent the same displacement vector, but in the cylindrical coordinate, we won't gonna use x, y, and z, we're gonna use r, theta, and z. So the displacement vector will be also ui delta I, the same index notation. But you should understand in this case that I will be once, I here will be r and theta and z. So it should be like ur, u theta, uz, like displacement along the radial direction of the cylinder, u theta, this is the displacement in the angular direction, uz, this is the displacement in the axial direction of the axis parallel to the axis of the cylinder. In the spherical coordinate, we're gonna have the u vector, which is gonna be also ui delta I, but in this case, we just gonna use I as once r and theta and phi. Instead of using I here as x and y and z, we're just gonna use it like r, theta, and phi. This is gonna give us the ur and u theta and u phi. So as you can see, still anyway, whatever you are working in rectangular coordinates, cylindrical coordinates, or spherical coordinate, in all the cases, this is rectangular coordinates, and this is the cylindrical coordinates, and this is the spherical coordinates, right? So no matter what the type of the coordinates, still you'd have three components of the displacement. It would be like x, y, and z, r, theta, and z, r, theta, and phi. No matter what, anyway, it's gonna be the same index notation even, and the vector notation for the same displacement field. But how about the gradient? The gradient, it is a vector, yes, but it will have a different form. It will have different forms. This gradient tensor, it will have different forms in the rectangular coordinate than the cylindrical coordinate than the spherical coordinate. For example, this nabla in the rectangular coordinate, nabla in the rectangular coordinate simply is partial by partial xi. This is what we defined nabla. It means that it's going to be like partial by partial x plus partial by partial y, delta x definitely, and this is going to be delta y plus partial by partial z, delta z, which can be written in the vector form as partial by partial x and partial by partial y and partial by partial z, like partial derivative with respect to x and y and z, right? So just this is simply a vector, right? Three components, very simple. This is the gradient in the rectangular, this is the gradient operator, this is the gradient operator in the rectangular coordinates, right? In the spherical coordinate, it will have a different form. It will be with this form. So the first component, the r component, here we are talking about the x component, the y component, the z component, because we do have delta x, delta y, and delta z, right? But now we do have delta r, this is the unit vector, and delta theta and delta z. These are the unit vectors in the cylindrical coordinates. So in the cylindrical coordinates, we are working in r and theta and z. So the gradient operator, there is some derivation for this form, but I won't gonna ask you to do it, or you can read about this one. Even I can give you material if you are interested to know what is the origin of this expression. From where did we get this? This expression? But anyway, there is delta r, delta theta, delta z, which is partial by partial r. This is the x, like the x component. This is the r component. This is the theta component. It is 1 over r delta by delta theta, and partial by partial theta and partial by partial. This is the z component. So these are the three components of the gradient operator. This is the gradient operator, but in the cylindrical coordinate. Make sense? In the spherical coordinate, we do have a different gradient operator. The gradient operator in the spherical coordinate is gonna be this one. So again, this is the gradient operator, but in the spherical coordinate, where we are using r, theta, and phi, which is gonna be a little bit different. Even the r component is very similar to the cylindrical coordinate. The theta component is very similar, but the phi component is different. There is no z component here. We do have phi component instead for the spherical coordinates. So this is the difference, but still the displacement vector is still three component. The gradient vector is still three components as well, but they are kind of different, right? So simply, if I ask you to form the strain in the cylindrical or even the spherical coordinates, what we're gonna do, we're just gonna work over the gradient. We're gonna do the multiplication of the gradient times the u. This is typically what we did for, this is typically what we do for the rectangular coordinates. We're gonna do the same here, but for the cylindrical and the spherical coordinates, right? But before we proceed, there are some things here that we should consider, that the partial by partial r of delta r, it should be 0. It's going to give us 0 vector. And the partial by partial r of delta theta and delta z, these are the gradients. These are the gradients or the derivatives of the unit vectors with respect to r. They're going to be zeros. This is some of the character of the cylindrical coordinates. But for example, the partial by partial x of delta x, it has a value, no problem. You got my point? It is not just 0, just 1. Or it's just delta x, to be more accurate, just delta x. And partial by partial y of delta y is going to be just delta y. And the partial by partial, or no, it's going to give us 0, by the way. Yeah, my bad. It's going to give us 0. The partial by partial x and the partial by partial y delta y equals 0, and the partial by partial z delta z give us 0. Why 0? Because there is no derivative for this one, it's just a constant. So it is constant with respect to, it is a unit vector, its value is just unit, or it's just one unity value, just 1. So its value is just 0, its derivative is going to be 0, the same thing here, 0, the same thing for the z is going to be 0. Very simple, right? So for example, like the partial by partial z delta r, z delta theta, z delta z is going to be 0 as well, right? Except for the partial by partial theta. Delta r is going to give us delta theta, partial by partial theta delta theta is going to give us negative delta r, and the partial by partial theta delta phi is going to give us 0. These are the characteristics of the derivatives of the unit vectors in the cylindrical coordinates. You're gonna find very similar things for the spherical coordinates. In the spherical coordinates here, I'm sorry, these are for the spherical. So these are the characteristics of the Very similar thing. Where is it? Yeah, okay. For the cylindrical coordinates, yes. So the derivatives of delta r, delta theta, delta z with respect to r or even z, they are zeros. But with respect to theta, it is different. Delta theta, negative delta r, and delta z is going to be zero. These are for the cylindrical coordinates. The derivative of the unit vectors in the spherical coordinates, they're going to be a little bit different. Very similar in some things. Like, for example, the delta r, the derivative of delta r, delta theta, delta phi with respect to r, it's going to be zero. But with respect to theta or phi will have values, except like delta theta by delta phi equals zero for this spherical coordinates. Make sense? So we're going to use these things here in the formulation of the, or driving the strain in, or writing the strain in the cylindrical coordinates. So let me remind you very quick with something regarding the gradient operator in the rectangular coordinates. So in rectangular coordinates, x and y and z, nabla, it had been defined as partial by partial x delta x plus partial by partial y delta y and plus partial by partial z delta z, right? So simply, if we are interested in finding nabla u, which is the gradient of the displacement vector u, in terms of the index notation, this is going to be partial by partial xi delta I, and we're going to have here the uj delta j, right? So as you can see, this delta, we can carry on the delta I. We can just write delta I, this delta I, it can be written here, no problem. This is originally. So this derivative, the derivative operator is going to affect both the uj and the delta I, both of them, not just uj or just delta I. So this means it can be written in this form. I can write this one as first like delta I, then I'm going to have the partial by partial xi of the multiplication of uj delta j. This is like the multiplication of two functions. So to split this one is going to be split into delta I times the partial by partial xi uj, make sense, times delta j plus the uj times the partial by partial xi delta I. You got my point? Like you're gonna split it into two terms. Now let us work over, as you can see, we do have here the gradient or the derivative of uj times delta I, which is a unit vector. Then we do have here in this term the derivative of delta I, which is the unit vector. So let us work on the derivative of xi, which is the unit vector, as delta I. Just this one. And we are working in the rectangular coordinates. So to split this one, it's gonna be splitted. This gonna give us here. This is gonna be splitted into this one. It will be split like partial by partial x delta x plus partial by partial y delta y plus partial by partial z delta z. Why? Because I is a dummy index that it should be repeated. So you're going to consider once x plus y plus z, right? Some of the characteristics of the rectangular coordinate, that the derivative of delta x, the unit vector x, is equal 0. This term equals 0. The derivative of partial by partial y delta y also equals 0. Partial by partial z equals 0. So we're going to end up with just equals 0. So that's why this term will be cancelled. Then we're going to end up at the end. We're going to end up that this is going to give us at the end, the nabla u is going to give us only the first term, which is going to be partial by partial xi uj delta I delta j, which is going to give us the tensor. This is the conventional tensor that we used to use for the, or define for the gradient of a displacement. But you should understand there should be another term, but because the derivative of this term, or this term that include the derivatives of the unit vectors, and the derivative of the unit vector in the rectangular coordinate is 0. So that's why we didn't discuss this term before. This is when we are working in the rectangular coordinates. But in the spherical coordinates or cylindrical coordinate, there is a derivative to the unit vector. Like here, for the cylindrical coordinate, there is a derivative for the unit vector. The same thing for the spherical coordinate. So that's why this term should be considered when we derive the gradient of a vector using in the cylindrical coordinate or the spherical coordinate, as I'm going to show you. So for example, let us work in the cylindrical coordinates, which is r, theta, and z. Make sense? We defined above here that nabla, which is the gradient, it had been defined with this form, right? Which is partial by partial r plus delta theta 1 over r partial by partial theta plus delta z partial by partial z. So so simply I can write nabla u as the multiplication of two terms. The first term is delta r partial by partial r plus delta theta 1 over r partial by partial theta plus delta z partial by partial z. This is the unit vector. These deltas are the unit vector. This is just nabla times u, which it should be the ui delta I or uj delta j. It doesn't matter. You can even use it like ui delta I or uj delta z. Then now we're going to do the multiplication of this term times all of these three terms. So starting with the first term here, this is going to give us like delta r. Then we're going to have here the partial by partial r of ui delta I, both. This is going to be split into two terms, plus the delta theta 1 over r times the partial by partial theta of ui delta I. The same thing for the third term, which is delta z, the partial by partial z of ui delta I. Now let us work over all of these three terms, starting with the first term. Here equals delta r. This term, it will be split into two derivatives. So it's going to be like partial ui by partial r delta I plus the ui partial by partial r delta I plus this is for the first term. It has been split into two terms. The same thing for delta theta 1 over r. Then we're gonna have like a square bracket of partial by partial theta of ui delta I plus the ui partial delta I by partial theta. And the third term is gonna be the delta z times the two derivatives of partial by partial z ui delta I plus the ui partial by partial z of delta I in this way. So as you can see, there are some derivative of the unit vectors like this term. This term is a derivative of the unit vector with respect to r. This is a derivative of the unit vector with respect to theta, which is this term, and this term is a derivative of the unit vector with respect to z. For the rectangular coordinates, all of these derivatives were zeros. But for the cylindrical coordinate, these derivatives, they do have values. So for example, let us work on the first derivative here on the side, like partial by partial r of delta I. Delta I, it will be split into like r and theta and z. So this is going to be split into like partial by partial r of delta r plus partial by partial r of delta theta plus the partial by partial r of delta z. And referring to this equation here, like the partial derivative of delta r, delta theta, delta z with respect to r, all of them are zeros. You got all of them, they're gonna be zeros. So it means that this means, or in other words, it shouldn't be summed, by the way. Like this one is gonna give a vector because partial by partial r delta I, this is gonna give us a vector. So we're gonna end up with like three different values. one value for the partial by partial r delta r, and partial by partial r delta theta, and partial by partial r delta z equals. All of these are zeros according to the above equation. Make sense? So what does it mean? It means delta r, delta I, this is gonna give us definitely zero. All of this term will be cancelled. The same thing applies to the partial by partial z delta I. Partial by partial z delta I, this is gonna give us like three different possibilities or three different values. Partial by partial z delta r, partial by partial z delta theta, and partial by partial z delta z, where I, it should be r theta z. This is gonna give us zeros. All of them are zeros according to this equation that we said here. The partial derivative of r theta z with respect to z equals 0. But the partial by partial theta, it will have a value for either for partial by partial theta delta r and delta theta, but for delta z is going to be 0. So let us investigate this, do the same, for it means that this term will be definitely 0. Then how about the partial by partial theta of delta I? Again, it is going to be split into, we do have three possibilities here, three values. The first value is partial by partial theta of delta r, and partial by partial theta of delta theta, and the partial by partial theta of delta z. According to the above equation, partial by partial theta delta r gives delta theta, and delta with respect to delta theta with respect to theta gives negative delta r and 0 for the delta z. So it means that we're gonna have here delta, going down here we're gonna have here delta theta, negative delta r, but 0. Make sense? So going back again to this term, it means that this derivative will have two values. So what does it mean? It means that this term is going to be split into two other terms. If there is a third value, it will be split into three terms, but this third value is already 0. So what does it mean? I can write, I'm just gonna write this term here, this one, just big this one, which is ui delta partial by partial theta delta I. This is gonna be split into three terms initially, like u r partial by partial theta delta r. The first term is just assume r, I is r, plus the second term is gonna be u theta partial by partial theta delta theta. The third term is gonna be uz partial by partial theta delta z, right? This term we got it 0. This term is 0, right? This term, this derivative give us negative delta r. This derivative give us delta theta. So what does it mean? It means that this term we're gonna end up with ur delta theta negative u theta delta r. Make sense? So substituting all of this data here. So the first term is gonna be just delta r partial by partial ui delta r. It means that you can multiply delta I delta r together. So we're gonna end up, this gonna give us the nabla will be equals the the first term will be delta r delta I, the partial ui with respect to the with respect to r, right, with respect to r, plus the second term it became 0. How about this one? This is gonna give us delta theta 1 over r times this term. So it's gonna be delta theta delta I 1 over r, the derivative of ui with respect to theta. So this is gonna give us the delta theta delta I, the 1 over r of partial ui with respect to theta, right? This is gonna give us the first term plus the second term. The second term, it has been split into just two terms, so it will be multiplied plus the delta theta. Delta theta, if you just multiply delta theta 1 over r times this term, which is ur delta theta negative u theta delta r, right? This is gonna give us the second term. The third term is just gonna be delta z times delta I partial ui with respect to z. So delta z I partial ui with respect to z. This is gonna give us the third term. So this at the end is gonna give us the derivative or the gradient, I'm sorry, the gradient of the displacement, but in the cylindrical coordinate, how it's gonna look like, which is already given up here, that the gradient of the displacement field, first this is the gradient operator, this is the displacement field, this is after the calculation. After we did all of this simplification, we're gonna end up with this expression for the displacement. As you can see here, you're gonna find for the delta theta, for this term, if we did here, we're gonna end up like, yeah, this term is gonna be UR over R, delta theta, which is this one, negative delta theta delta R of U theta over R. Okay, because this is gonna give us the negative delta theta delta R. Yes, delta theta delta R of U theta over R. So these two terms are this part. All right. So this is the nabla U. How about the nabla U transpose? The transpose of this term, your objective is just to switch these i's. Just switch this delta I, instead of having delta R, delta I is going to be delta I, delta R, and delta I, delta theta, and so on. If you just switch, it means that you're going to end up with the transpose of this one. And then if you add it, this is going to give us the U nabla, which is just replace the I and R, replace the I and R, okay, here, just switch the R on I, we're gonna end up directly with the transpose for the cylindrical, this is just for the cylindrical coordinate. If we sum this one plus this one times half, this is gonna give us the strain tensor. So simply, if you added this, all of these terms to these terms, here, we're gonna end up with this expression for the strain using the index notation. If we decided to write this one in expanded form, write all the components like epsilon RR. Here, the components of the strain should be epsilon RR, epsilon theta theta, epsilon ZZ. This is like epsilon XX, epsilon YY, epsilon ZZ in the rectangular coordinate, but these are in the cylindrical coordinate. Then we're gonna have epsilon R theta, epsilon R Z, and epsilon theta Z, and epsilon theta Z. This is like XY, XZ, and YZ. So these are the 6 components of the strain. To write them explicitly, we can write them or derive them from this compact expression, as I'm gonna show you. For example, if we plugged I as R into this expression, we're going to end up with epsilon RR, because if, as you can see, we do have I's and R and theta and Z. So your objective is just to plug R, epsilon, just collect the R terms, RR. For example, to write epsilon RR, just collect any delta R, delta R. Collect any term that include delta R, delta R. For example, with the first term, so here I'm just going to write how we can drive the epsilon RR with this term. The first term, we do have 1 over 2. We do have delta R. Now I'm going to consider I as R as well, because I, it would be R and theta and Z. It means that this term, it's going to be split into 3 terms. This part is going to be split into 3 parts or 3 terms. But here I'm interested in just delta R, So I'm going to consider delta R because I'm working as RR. So delta I, it will be R, so this is going to give us the partial if U R with respect to R, plus delta R, I'm going to consider I as R, delta R, the partial if U R with respect to R. Right, this is the first term. Here we do have theta, but I don't have theta. I'm interested in RR, not theta R, for example. For example, I, it would be R. So I do have R theta. I do have theta R, I do have theta theta, theta Z, but I don't have RR. So this term will not be included in epsilon RR. The same thing here. I'm interested in RR, so I do have R theta, I do have theta theta, I do have Z theta, but I don't have RR. So this term will be excluded. It means that this term will be 0 with respect to the epsilon RR. The same thing for the other. Here we have theta theta, there is no R's. R theta, theta R, or R theta, both won't gonna work for us because we need RR, ZR or RZ, it won't gonna work. So the only term that will be included from this expression are just these two terms, which are gonna give us at the end. If you sum these two because they are identical, you're gonna end up with the partial by partial UR delta R delta R delta R delta R delta R, which should be like delta R here. So this one will be cancelled with this one, like, so it means that we're just getting the component. So this is the RR component of the strain. The same thing can be applied if you just follow the procedure to the all the other components. We're gonna end up with the same value, right? Like for example, let us choose here theta theta. You're gonna do the same. There is no thetas here, there is no thetas here, there is R, so these two terms will be excluded. But there is theta theta, there is an option of theta theta in case that I is theta, so you're gonna substitute for you I is theta. Here I should be theta to have theta theta, so this should be theta, and so on. If you carry on the same way, you're gonna end up with this expression for epsilon theta theta. The same thing for epsilon zz. For example, for epsilon r theta, here we do have r first, r theta, but r first then theta. But you should understand that this strain, it is a symmetric tensor, so the r theta, epsilon r theta should equal to the epsilon theta r. You got my point? But you just gonna now let us focus on r theta, just r theta, just r theta. It means r first then theta. So to find this component, this element here, the r it should come first, then theta. So this should be theta using the I should be theta. So this term, if we are interested, I'm just gonna write it up here. So for example, epsilon r theta, it's gonna be, the first term is 1/2 times delta r delta theta. I needed theta, u theta with respect to r, plus I, it can, for example, I, it would be r theta and z, but I need r first. I can use theta, yes, but this one, it is not first. I mean, I need the r, it should be the first one. So this term will be excluded, will be 0 with respect to the epsilon r theta. It means that this term will be cancelled, plus the second term, I need r first, delta r first. There is no delta r first. Here we can have delta r first, right? So if you use this one as I, as r theta, because we needed r then theta. So this term, it can be considered as half, there is half as a common factor, delta r, delta theta of 1/r partial u r with respect to theta, because you're gonna use I as theta. Make sense? And this one will be excluded. The third term, there is theta theta, we don't need it. We start with theta, no, it won't gonna work. We start with r, yes, this term should be considered. This term is a negative 1/2 because we need r first then theta, so it's gonna be negative 1/2 times u theta over r as delta r delta theta, right? Then we do have z, then here we do have, we could have r first, but with z we don't need it. We need r then theta. So these are the only terms that should be considered here. So if we get rid of this delta r delta theta, delta r delta theta, delta r delta as a common factor that indicate, because we should have here delta r delta theta, so what should be the element? The component of this tensor, which is epsilon r theta, it should be 1/2. You can consider even 1/2 as a common factor, partial theta by partial r, 1/r partial r ur with respect to theta, negative u theta over r, which is gonna give us this expression, which is theta with respect to r, ur with respect to theta, and this is the half as a common factor, negative u theta over r. If we did the same, we can do the same for the other component. You're gonna end up directly with the components, the strain, the sixth component of the strain. And even if we tried r then theta, how about if we switch theta then r? If you tried up there, you're gonna end up with the same expression. This means that this formula in the index rotation is correct. So this is the strain in the cylindrical coordinates, and these are the explicit forms of the six components of the strain tensor, we can do the same even for the rotation tensor, but you should understand that the rotation vector, for example, the rotation vector, it should be the half of the curl of the displacement. It is half of the curl of the displacement. This is for the rotation vector in the cylindrical coordinate. In the spherical coordinate, is going to be the same procedure. Just the only different thing is just the expression in the gradient operation. This time, instead of using z, we're going to use the partial by partial phi, and we're going to have some sine theta in addition to r. Again, this form has some derivation, but I didn't explain this one to you because we are not interested in it. We are interested in elasticity and strains and these kind of things. But it is important to know how we can represent the strain in the cylindrical and spherical coordinate. So if we plug this nabla and we substitute it and we calculate it, then you can calculate the nabla. You can simply calculate the nabla u and substitute with this nabla, with this expression, and do the multiplication the same, and then you're gonna consider these relations of the derivatives of the unit vectors. You're gonna end up with a certain expression for the nabla u. Then you're gonna take the transpose as we did with the cylindrical coordinate to end up with then you're gonna add the nabla u plus u nabla times half. This is going to give us the strain tensor, which can be explicitly written. These are the 6 components of the strain in the spherical coordinates. So I'm going to keep this one at home for you to prove that the strain in the spherical coordinate, the component of the strain in the spherical coordinate is going to be represented in this way. If you did the same as we did for the cylindrical coordinate, you can easily derive these things. Okay, this expression. So these are the components of the strain. So what we discussed generally so far, I represented to you the component of the strain in the rectangular coordinates, and this is what we mainly gonna use. But in some types of problems, it is advised to convert to cylindrical or spherical coordinates. So these are the expression of the strains in the spherical coordinate, and these are the expressions of the strain components in the cylindrical coordinates. Make sense? Now let us move to another topic, which is the compatibility equation. So before we go through the compatibility, the example that I explained before, example 1, that we started from the displacement field, then we drive the strain and the rotation tensor. Generally, as even we have discussed this one very quick through the equation of motion, but we're going to go over it again with more detail when we discuss the equation of motions or the equilibrium equations of continuum, with more details. Like in the continuum mechanics, generally we are interested in the strain tensor. The strain tensor is the most important tensor because we are interested in observing the changes in the dimension and the shape of the object due to the external force, and we don't care that much regarding the rotation of the object, because the rotation of the object, it is conjugate to the moment of the force, and the moment of the force equation, if you remember from the equilibrium or equation of motion, was 0, indicating that the skew-symmetric part of the stress tensor, it should be 0. So we're going to go over this part again, and I'm going to demonstrate to you that the rotation tensor is not important to us as the strain tensor. We need the strain tensor in terms of the deformation of the continuum to describe the deformation. But generally we said that the deformation, the deformation tensor, which is the gradient of the displacement, it has 2 parts. One is symmetric and the skew-symmetric. The symmetric part refers to the change in dimension and shape. The skew-symmetric is just the rotation tensor. In the example that I solved, as I mentioned, we started from the displacement field. Then from the displacement field, we can form the strain tensor or the component of the strain simply by doing some derivative, right? Then we can plug with the coordinates of a point to end up with the strain at different points that belong to the continuum, no problem. So this example is a straightforward exercise. It's a straightforward problem, no problem with this one. But how about if the strain is given and we are interested in finding the displacement, the inverse problem, like we already reversing, or the inverted problem, like the strain is already given. And remember, the strain is 6 components, and we are interested in finding the displacement from the different strain fields that already provided to us. The displacement components, the components of the displacement vector are only 3 components, but the strain, it has 6 components. So the strain in terms of the displacement is it is 6 equations, and we have to solve these 6 equations to find the displacements. But this system is over-defined. It means that the number of equations is higher than the number of the unknown. The unknown is just 3 displacements. We are seeking 3 displacements for given strains. So we're going to end up with, we have 6 equations of the strain in terms of the displacement. It means that the system of equation is over-defined. It means that we already having lots of equations, 6 equations, and we're just seeking 3 unknowns, right? So the task of computing the strain, which is conventionally the strain type that we're already discussing, is the infinitesimal strain, and we're going to go over this one when we discuss the linear elasticity. From a given displacement field, like the displacement is given and we are computing the strain, it is a straightforward exercise like exercise number 1 that I explained above. But how about if we are interested in finding the displacement from a given strain field? This is not a straightforward method because there are 6 independent partial differential equations. The strain, it has 6 components, and we're going to end up with 6 ODEs or 6 partial differential equations that should be solved for just 3 unknowns. So it means that the system is already over-determined solution or over-determined system of partial differential equation. Make sense? So the question is how we can solve this system. Basically, you already given 6 equations, so you can use any one of these 6, just 3 equations and find the displacement. That is fine. But you should understand that if you try to use, for example, I do have say 6 equations. I can use the first 3 equations to find the 3 unknowns. How about if I try to use the other 3 equations? Should I get the same 3 unknowns, or it would be different? If you got different unknowns, it means that you have multiple solutions. It means that this system of partial differential equation does not provide a unique solution of the displacement field. And in this case, we're going to say that the strain field, it is incompatible. So here we do have the compatibility. Compatible, it means consistent. What does it mean consistent? It means that if you try to find the displacement or use any one of the 3 equations, any one of the 3 components of the strain to drive the displacement field, you should end up with the same displacement field if you try to use any other 3 components or the other 3 components of the strain. If this happens, this indicates that the strain field is compatible. The compatibility of the strain field, it has a physical meaning that I'm going to explain, but for now, this is what I'm talking about, is just mathematically things. Mathematically speaking, a compatible system of equations or consistent system of equations, especially in case that it was over-determined system that would provide over-determined solution, that, as I mentioned, like if you try to solve 3 equations of the 6, you're going to end up with a displacement field that it would be different than the displacement field if you try to solve the other 3 equations. If this happens, this means that the strain field is incompatible. But we need it compatible. We need the strain field, it should be compatible. If we try to use any 3 equations, we should end up with the same unique displacement field, ux, uy, and uz. So this gives us the Sand-Venant valence compatibility equation. This is known as the Sand-Venant compatibility equation, or just directly the compatibility equation. We can use this equation that to make sure that our computation of the displacement field are unique, like we're gonna end up with a unique displacement field. This is in case to prove that the strain field is compatible. There are some conditions to prove or to investigate whatever the strain field, the 6 components are consistent together. Consistent or compatible, it means consistent together to give a unique displacement field. If they are consistent and they're gonna use using any 3 equations, you're gonna end up with the same displacement field. It means that the strain field is compatible and it can satisfy a certain condition known as the compatibility equation. So the compatibility equation, it is like a measure, like a test. Like we test whatever the displacement field for a certain continuum, is it compatible or not? In terms of continuum mechanics, generally speaking, for any continuum, its strain field, it should be compatible. If it is not compatible, it means there is something wrong. And this is not a continuum mechanics, kind of. So here we are talking just mathematically things. Then I'm gonna explain to you what does it mean, the compatibility conditions for the strain. But before that, let me show you how we can drive these compatibility equations. So let us consider the strain fields over a two-dimensional space, like in two-dimensional strain field. Let us work in just two-dimension in the rectangular coordinate, like we do have only x and y, and there is no z. It means that generally we do have 6 components of the strain. Some of this component will have like epsilon z z, epsilon x z, epsilon y z. These 3 components that include z will be zeros. This is a note, like we're already working in two-dimensional instead of the three-dimensional thing. Like assume that we're already working in 2 dimensions, so we should have epsilon xx and epsilon xy and epsilon yy. There is no any z's. These are, so we're gonna end up with just 3 components. And in 2 dimension, we do have only 2 displacements, right? We do have only ux and uy. Assume this one. Why am I choosing 2 dimension? Because this is simple. We can work in the 3 dimension. We're gonna end up with the same result, but I just want to show you something here. Just for the sake of simplicity, so you could understand me, let us just work over 2 dimension, but we can repeat the thing for the 3rd dimension by including the z direction as well. So for example, what should be the equation of the epsilon xx? Epsilon xx is already ux comma x in terms of the displacement. If you just go up, you're gonna find that the epsilon xx is already ux comma x. Epsilon yy, we drive it as the y comma y, and the epsilon xy, we got it by 1 over 2 the ux comma y plus the uy comma x, or uy comma x plus ux comma y, doesn't matter. So we're gonna end up with 3 equations in just 2 unknowns. So this is over-determined system, right? Like we do have just 2 unknowns, ux, uy, nothing more, but we do have 3 equations. So it means that if these 3 strain fields, if these 3 strain components are consistent and compatible, there is a condition that we would like to drive here. If they are compatible, we should end up with the same solution, with the same ux, uy, no matter what, which 2 equations that you're gonna use. Any 2 equations, you're gonna end up with a unique ux and uy. So we can write these equations, since we are interested in solving us, we can write these 3 equations into this form, like ux comma x, ux comma x, it should equal to the epsilon xx. Remember, epsilon xx will be given in this case, so this is gonna give us the first equation, and uy comma y, it is gonna be epsilon yy, and this is gonna be the second equation, and the ux 1 over 2, or we can simply write ux comma y plus uy comma x equal double xy, which is gonna give us the 3rd equation, right? Just multiply the 2 on the other side. So these are 3 equations in just, but partial differential equation in just 2 unknowns. So this is over-determined system. We would like to check the compatibility of this strain field, whatever it is, compatible or not. So we would like to drive here the compatibility condition, or the compatibility equation. So the compatibility condition, can be driven simply by differentiating the first equation twice with respect to x, and the with respect to y, with respect to y, and differentiating the second equation twice with respect to x, and the 3rd equation, it will be differentiated once with respect to x, then with respect to y, or y then x. You got my point? So let us do the second derivative, find the second derivative of this equation 1 with respect to y. So this is gonna give us the ux, the second derivative of this one is gonna give us the ux comma x, then we're gonna differentiate twice with respect to y. So this is gonna give us yy again. So this is like ux comma x yy. It means that we do have 3 derivatives. This term can be written in this way, like the partial derivative of ux with respect to x with respect to y squared. But we said that before, partial by partial x, or partial by partial y, partial by partial y squared, this should be cubed here, right? Because this is 3rd derivative. It can be replaced by a comma for the sake of simplicity in terms of writing, right? So if we did these derivatives here, we can simply end up with like comma xxy equals epsilon xx comma yy. We're gonna do double derivative again with respect to y. This is gonna give us the first equation dash. The second equation, we're gonna do derivative twice, but with respect to x. So this is gonna give us y uy comma y xx equals epsilon yy comma xx. Double derivative with respect to x, and this is gonna give us the second equation dash. For the third equation, we're gonna differentiate once with respect to x and once with respect to y. So double derivative, yes, but with respect to x and y. So the first term, it's gonna be, the first term will be ux, or there is no need for the parentheses. It's gonna be ux comma y. Then we're gonna differentiate once with respect to x, once with respect to y, or y then x, it doesn't matter the order, plus the uy comma x then xy equals the 2 epsilon xy comma xy, because we are differentiating with respect to xy. This is gonna give us the third equation. Right? Then what you're gonna do, your objective is just to, as you can see, do you see the epsilon, the ux comma y xy? It means that you do have 2y and 1x. Here we do have 2y and 1x. It means that this term is typically the same like this term, right? And this term is typically the same like this term. It is y comma y, 1y, 2x, 1y, 2x. So simply I can get rid of the displacement and just substitute with the strains. So this term here, ux comma xy, y, this is gonna give us the epsilon xx comma yy, plus the uy comma yxx gives us the epsilon yy comma xx equal the 2 epsilon xy comma xy, and this is the compatibility equation. So if you already given a strain field, for example, if I give you a strain field, then I ask you to solve this strain field for the displacement field. Find the displacement field from the given strain field. And assuming that you're already working in 2 dimensions, like this case, you do have epsilon xx, epsilon yy, epsilon xy, and I required to solve for ux and uy. Before you solve, you should test, you should investigate, you should examine whatever this strain field that is given to you is compatible or not. Compatible to give a unique solution, or it is not compatible to give multiple solutions, and in this case it will not be accepted. We, in terms of continuum mechanics, we're gonna consider there is no solution for this problem. Right? So what is the condition is? This is the condition. This is known as the compatibility equation. This is the compatibility equation. Right? Or the compatibility condition. If the strain field epsilon xx, epsilon yy, epsilon zz, they are satisfying this equation, so we're gonna say that they are compatible, and the displacement field obtaining using any one of the 2 equations is unique. Make sense? This is known as the compatibility condition for the continuum mechanics. If we are working in 3 dimensions in general, this is just in 2 dimensions, right? This is just in 2 dimensions. We can write this one even using the partial. We can write this term as partial epsilon xx with respect to the y square, but this is the second derivative plus the second derivative of the epsilon yy, but with respect to the x square, equal the double of the second derivative of epsilon xy with respect to the x with respect to the y. So this is just in terms of the partial by partial, or in terms of the comma, which should be the same compatibility equation. So this is in 2 dimensions. In 3 dimensions in general, if we did so for the 3 dimensions, we're gonna end up with 6 compatibility conditions that connect or define the relation between the 6 components of the strain. So the compatibility conditions in the 3 dimensions, they are 6, not just 1. Okay, so it means that for the 3 dimension, this is for the 3-dimensional case, the general, and all of these equations are commonly known as the compatibility equation, like the second derivative of epsilon xx with respect to y plus the second derivative of epsilon yy with respect to x squared. It should equal to the double of the partial second derivative of epsilon xy with respect to x with respect to y. In addition, the epsilon xx and epsilon zz, they should be related to the epsilon xz. The epsilon yyzz should be related to the epsilon yz through this condition. So all of these are 6 conditions. All of them should be satisfied since we are working in the 3 dimension. So all of these conditions should be satisfied to achieve compatibility of the of the strain field to give a unique solution. As you can see, in 2 dimension we have only one equation as compatibility, one condition. But in 3 dimension we gonna end up with 6 conditions. Simply, if you try to cancel any z, if we decided to work in 2 dimension, if you try to cancel any z with a derivative with respect to z, so because we already cancelled all the z's, any term that includes z, it should be cancelled. Any term that includes z, it should be cancelled. There is z here, z on the denominator, there is z, which is epsilon z. So as you can see, all of these 5 equations will be excluded if we are working in 2 dimension, because in 2 dimension you're gonna have only x and y, there is no z. Any term that includes z, cancel this term. If we cancel these terms, we're just gonna end up with the one equation that we drive it for the 2 dimension. I will not ask you to drive this compatibility equation in the 3 dimension, but I can ask you to drive the compatibility condition for a 2-dimensional strain field. All right, but these are the compatibility equations, 6 equations that should be satisfied to make sure that this strain field, the 6 components are compatible together to give a unique solution of the displacement field. Make sense? These 6 equations can be written in the index rotation in a compact form into this form. This is the compact form in terms of the index rotation for the 6 equations, where m, n, and ij, either any one of these, like the n and m, can be x, y, and z. The same thing for the I and j, they could be x, y, and z. If you substitute once for m equals I and n equals j, the same xy, for example, and this is like xz or yz, you're gonna end up with 6 equations. As you just switch or change between these indices, you're gonna end up with the 6 equations that already written up there. So this is the compact form or in terms of the index notation. Also, we can write these 6 equations, these 6 compatibility equation, into another form, more compact form, which is that depend on the curl of the strain. So this equation, these are the compatibility equations using depending on the curl of the strain. The curl of the strain, which is nabla cross epsilon. If we started from this one, if we started from nabla cross epsilon, we're gonna end up with epsilon. This is the strain tensor. We're gonna end up with this expression where epsilon, these 2 epsilons are the permutation parameter, that it would be -1 or 1 or 0 depending on the indices. If you plug or use these ones, we're gonna end up with the compatibility condition, and this term definitely should be 0, right? Because this term, it should be the curl of the curl. It should be the gradient. I think the curl of epsilon. This should be the curl of epsilon, the strain, which is gonna be 0. This term is gonna be 0. It means that the compatibility equation is somehow related to the curl of the strain. Okay, so we could say that the compatibility equation, it is the curl of the strain, which it should be 0. Why? Because this nabla, the curl of epsilon gives a vector, and the curl of epsilon gives another vector, but there is an angle because the curl gives sine theta, and it gives the perpendicular axis. So this is going to give us the perpendicular axis, and if you try to find another curl to this axis, it's going to be 0, right? This is from the vector calculus. I won't gonna go through this vector calculus things for the curl, but I would ask you, for example, to prove that this double curl here, it's gonna give us this form or even this form, right? But you should understand that the compatibility equation, it would be represented in the explicit form in this way, or in the index notation form, or using the curl of the strain and the curl of the strain in this form, and it should be 0. Right? These equations, if you expanded this one, if we write this equation explicitly for I and J and K, where I, J, and K would be X, Y, and Z, we're gonna end up with the same 6 equations. Make sense? So what does it mean, a compatibility these compatibility conditions for the continuum mechanics. All right, so this is what I'm going to discuss now. So the strain compatibility, to explain it, let us consider that you have a material body, like any continuum body, whatever it is, like this one, for example. And let us, that we're gonna break it down into some small boxes or some small squares, lots of squares in this way, like you already working like finite element, for example, right? Lots of so many elements in this way, right? And then we're gonna choose some of these elements, or basically what we're gonna do, if this continuum is gonna be subjected into some forces, so it will be strained. Strained, it means that there will be some strain fields. There should be some deformation, and the symmetric part of this deformation tensor is gonna give us the strain. So we're gonna say that all of these elements, all of these boxes or squares, they're gonna be strained, but with different fields, because the strainer is a field. It means that it changes from one point to another point. Like within this element, the strain is different than this element, different than this element, and so on. Make sense? So assume that we do have this case, and we do have this element. So, and let us that we decided for some reason to give a strain to each one of these elements separately. Like we're gonna choose, pick one element, like they are separate. We broke down the continuum, this material body, into multiple elements. Then we're gonna pick each one of these elements and we're gonna give it like strain. Like you already injected it with giving it a shot, right? Injection, for example. Like you already injecting strain to each one of these elements. Then what happened if we decided to reassemble them back? So we already broke it down into multiple elements. We give each individual element some strains. Then we're gonna assemble them back again. If we try to assemble these elements and their strains, the strain that we give to each individual element, are not consistent together, definitely when they're gonna be assembled back, and you try to squeeze, for example, let us pick this element here in the middle, and we give this element a very high strain that is not consistent with the other strains of the other surrounding element, like these green elements. These are the elements that surrounding this purple element or pink element, right? Make sense? So if the strains in the green elements, in addition to the strains of this pink element in the middle, they are not consistent, and you try to squeeze and put this element in the middle of this continuum, it's gonna start to push the other element, resulting in excessive strain, more strain into the other elements. So we're gonna say that if this happens, this means that this element, its strain is not consistent with the other strain. But for some reason, if we give the strains to all of these elements and we try to reassemble them again, and they're gonna fit perfectly together without any further straining or any excessive straining, and they're gonna fit together perfectly, we're gonna say that we do have consistent strains or compatible strains. This is the physical meaning of the compatibility. We are using the compatibility things in this compatibility condition in lots of things, like in finite element modeling. In finite element, for example, the compatibility is a big deal because we're already doing so. We are breaking it down in the finite element. We are breaking the element into different elements. So the strain within any one of these elements, in comparison to the strains of the surrounding element, they should be compatible together. Like you already reassemble these elements back again in the continuum, so they should fit without any excessive, without squeezing, without pushing. They can easily fit together to, in case that we do have compatible strains, right? So this is an essential thing in continuum mechanics. In continuum mechanics, to have a continuity and a continuum without any excessive strains, if we assume that we're gonna break it down and we're gonna consider for each one of these elements the strain over these elements, when we try to assemble them back again, they should fit together to indicate a compatibility, and this is highly important condition that would be used in different applications. If there is an opening or a crack or something, there are some compatibility conditions that should be satisfied here to make sure that the displacement field Because of the compatibility condition, if we try to find the displacement field based on the strain of this element, it should be the same displacement field based on the strain of this element over the edge. For example, if we are interested, we have here two elements and they are common together, they are sharing the same edge. So the displacement field over this edge, whatever you're gonna calculate it from this element or this element, it should be the same. Otherwise, you're gonna have a crack. It's gonna show up here. If this edge, if you try to find a displacement field from this element, so you're gonna have an edge that is different than the edge of the other element. So it means that there is a cavity here. There is something empty space, right? It means there is something wrong in the solution in this case, and this is not working good with in terms of the continuum mechanics. So the compatibility over the strain, it is a big deal, and this is the meaning of the compatibility again, and we are using either out this compatibility equation to evaluate the compatibility of the continuum in different applications in linear elasticity or in continuum mechanics in general. Make sense? Now we're gonna move, I'm gonna give you some examples here on using these compatibility conditions, and especially to know how we can find the displacement field from the strain field under this compatibility condition. We practiced before how we can, starting from the displacement field, how we can find the strain. Then here we are talking about the inverse of this problem, the inverted problem, like the strain is given and how about the displacement field. So if we consider this example here, this is the second example in today's lecture. Given the two-dimensional infinitesimal strain field, this is the strain field epsilon xx, epsilon yy, and epsilon xy, given as functions of x and y, there is no z's at all. It means that we just work in two dimension, where c1, c2, and c3, these are three constants. And we are required to examine whether the strain field is compatible or not. And if it is compatible, what is the condition for the compatibility that connects this C1 to C2, C3? So simply the compatibility condition for the two dimension, this is the one that we drive it up there, right? Which is the first equation. Like the second derivative, which is epsilon xx comma yy plus epsilon yy comma xx, it should equal to the double of the epsilon xy with respect to the xy, comma xy. So this, it means that for the two-dimension problems, we do have the epsilon xx comma yy plus the epsilon yy comma xx, it should equal to the double of epsilon xy comma xy, right? So your objective is just to do the derivative, find the epsilon xx comma yy, how much it is. The second derivative of epsilon xy, xx with respect to the y. So we do have C1 times x is constant, is a common factor, right? Because we are differentiating with respect to the y. So the first term, it has no derivative with respect to the y, but the second derivative of y squared with respect to y gives 2y, then 2. So this is going to give us just 2, right? Because the first derivative is 2y, the second derivative is going to be 2. So it means that the epsilon xx comma yy is gonna give us at the end 2 c1x, right? How about the epsilon yy comma xx, the second derivative of yy with respect to x? So there is derivative with respect to x, and there is twice derivative even with respect to x. So you're gonna do this, is gonna give us the 3 times 2 over 3 c2 x. This is the second derivative with respect to x, which is 3 can be cancelled with the 3, so we're going to end up with just 2. So we're going to end up here with 2 c2x. Make sense? How about the epsilon xy with respect to x, then with respect to y? So let us find it with respect to x first. The epsilon xy with respect to x give us 2 c3y x, right? And then the epsilon xy with respect to comma xy, we're gonna differentiate one more time with respect to y. This is gonna give us the 2c3x. Make sense? If we arrange these three terms into this equation, this is the compatibility equation. Just substitute into equation 1. So substitute into equation 1. We're gonna end up with this relation. Epsilon x x y y gives us 2c1x plus the epsilon y y comma x gives us 2c2x. The double of epsilon gives us the equals. On the right side is going to give us 2 times this term, right? So it's going to be 2 times 2 gives us 4c3x. Make sense? Simply we can cancel the 2 with the 2 with the 4 to give us just 2 here, right? And then the x can be cancelled with the x with the x. So we're going to end up that this system, this strain field, is compatible to each other under this condition. What is this condition? That C1 plus C2 should equal to the double of C3. It means that if this condition, it means that if these constants within the strain field, they are not satisfying this equation, this strain field will not be compatible. This is the condition of the compatibility. This is the relation of the constant to each other to have this strain field compatible. Make sense? There is an example here on the driving the displacement field from the strain field for this problem, but this requires lots of mathematics. So I'm gonna skip this one for now, and then I'm gonna cover this one. We're gonna go over it again one more time for the when we cover the two-dimensional problems, and because we have to go over some mathematical things to know how you can solve partial differential equations in 2 dimensions. So I'm gonna skip this one for now, and in the future we're gonna consider it definitely. This example we started from, in this example we have to start from this given strain field, and from the strain field we have to drive the displacements ux and uy, the displacement field from the strain field, that after we satisfy the compatibility conditions. So we're gonna consider these things but later, especially when we discuss the 2-dimensional problems. So that's it for today's lecture. Today we discussed intensively the kinematics of continua. We discussed the deformation, the strain, the rotation tensor, the rotation vector, how we can drive them. We even discussed the strain representation in cylindrical and spherical coordinates. Then we discussed the compatibility equation, their importance, and why we should consider these compatibility conditions in the continuum mechanics. The next meeting we shall be moving, or we are going to discuss the stresses, the stress and the constitutive equations and the equations of motion, and we're gonna go over the stress transformation very quick as well. All right, so that's it for today's lecture, and thank you, and see you in the next video.